So this is the 41st session on relative velocity. In this I will take up one more problem on two-dimensional relative velocity collision problems in which A relative is non-zero. Okay. So I'll write down the question. So after this next video onwards I'll be making videos on relative velocity translating frame problems. Okay. 2 or more frames in mutual translation. So in this I'm going to take up this. Okay. Fine. So two-dimensional relative velocity collision problems. Last video on this topic in which A relative is non-zero. I write down the question, okay? P1 and P2 are two moving points. Are 2 points which are initially situated. P1 and P2 are 2 points which are initially situated at 0, 0 and 0, L respectively. P1 and P2 begin to move with same constant speed v. P1 moves along a straight line. P1 moves along x-axis. Moves along x-axis, positive x-axis. And P2 moves such that at any instant its velocity is aimed towards P1. Aim towards P1. At a certain instant t, the line joining P1, P2 makes an angle of theta with the positive x-axis. Line joining P1 and P2 makes an angle of theta with the positive x-axis. And D is the separation between these 2 points at this instant. D is the separation between these 2 points at this instant. Find D in terms of L and theta. Find D in terms of L and theta. Find D in terms of क्या? L and theta. Alright. This is okay. So I'll draw the diagram, okay? This is the x-axis. This is the y-axis. Initially P1 is here, origin. Initially P2 is here, 0, L. This distance is just L. P1 moves along positive x-axis at a constant speed v. and P2 moves at a constant speed v such that its velocity is always aimed towards P1. At certain instant t, P1 is somewhere here. Till that instant P2 has moved something like this. It is somewhere here, it's moving at a speed v. P1 is moving at a speed v. This is the angle theta. At time t, P2 is somewhere here. This is P1 at time t. This is P2 at time t. And now distance between P1 and P2 at this instant is d. Okay. Now d we have to find in terms of L theta. We have to find the value of d. Alright. We have to determine d in terms of L and theta. In terms of L and theta, we have to determine the value of d. Alright. Now, how do we determine that? That is the question. So instead of d, just let's write r, okay? I'm denoting d by r, just because d of d I don't want to write. Again, and at the end I'll replace it by d. Okay, just for convenience, nothing else. So r is the separation between these 2 points at time t. Alright. So now question is how to find the value of r in terms of d and theta, in terms of L and theta. So first of all, we use the concept dr by dt, rate of change of r with respect to time, that is rate of increase of r minus rate of decrease of r. Now component of v along this line is v cos theta, this will get to increase r. So rate of increase of r is equal to v cos theta, and rate of decrease of r, that is just equal to v itself, because v will tend to decrease r. Alright. So now dr by dt is equal to this much. I multiply by dt. So dr becomes v cos theta dt minus what? v dt. Now integrate this equation on both sides. 0 to capital T. 0 to capital T. Initially r was L. At time capital T, r becomes what? R. Integrating, inserting limits r minus L. V is constant, v comes outside the integral. Cos theta dt 0 to t. V is outside, 0 to t. So r minus L is equal to v times 0 to t cos theta dt, and this is just vt. First equation we have obtained. Now we have to eliminate this integral, then the problem will be solved. Now see, at time t, coordinates of P2 are say x comma y. Okay. So this distance, if we drop a normal from P2 on y axis, this distance x. If we extend here, this distance also x. This is r, this is theta. Theta is also theta, opposite angles. This distance is just equal to r cos theta. And this distance is just the distance moved by P1 in t time, which is simply Vt. Alright. See here capital T, when this capital T is just general small t itself, so I have used a different symbol, okay. So from this we see that this plus this equal to this, r cos theta plus x is just equal to how much? Vt. Okay, fine. So now see, P2 is here at time t. This is theta. Draw a line through P2 and parallel to x-axis this theta. So this angle also with theta. Okay. So velocity of x component of velocity of P2 is v cos theta. There is dx by dt. So dx by dt is just equal to what? V cos theta. So from this dx will be how much? V cos theta into dt. 0 to capital T. 0. X will be how much? Vt minus r cos theta. Of this equation. So Vt minus r cos theta. V is constant. V comes outside the integral. Cos theta dt. 0 to what? T. This integral I substitute in this one. Then we get r in terms of theta. Alright. I'll rub this, okay. So this integral I replace in this. I eliminate these two integrals. From this equation we see that this integral can be written as r minus L plus Vt by V. This side r minus L plus Vt by V. This can be written as Vt minus r cos theta by V. V and V will go away. R minus L plus Vt is just equal to Vt minus kya? R cos theta. Vt will go away. R comes this side, L comes this side. R into 1 plus cos theta is just equal to L. L by 1 plus cos theta is just D, which is replaced by R. So this is therefore the required answer. Fine. So here, till here, relative velocity in 2-dimension problems. Relative velocity problems for collision in 2 dimension. This has been fully discussed. Fine. This was the 41st session on relative velocity. So in this till this much I have fully discussed the relative velocity collision problems, phase 1, phase 2 both. Phase 1 started from 34th video and ended on 41st video on relative velocity on phase 2. So from 34 to 41, that is how much? 8 videos. 8 videos on relative velocity 2-dimensional collision problems I have taken. All types of problems I have discussed. If you go through them, revise it properly, and then try numericals from some other source, definitely you are going to benefit. I don't think there's any doubt about it. Fine. So I close it here itself. Alright? Fine.